In the strange world of quantum mechanics, two particles can interact and become mathematically linked, sharing a single state. If you measure the properties of one particle, like its spin, the other particle instantly adopts a corresponding state, no matter how far apart they are. Albert Einstein famously hated this idea. He argued that since nothing in the universe can travel faster than the speed of light, this instantaneous connection had to be impossible, dismissing it entirely as spooky action at a distance. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper arguing that quantum mechanics had to be an incomplete theory. They proposed that these particles must contain hidden variables, secret, pre-programmed instructions that dictate how they will behave when measured. You can think of their argument like a pair of gloves. If you pack a left glove and a right glove into separate boxes and send one to Tokyo and the other to New York, opening the Tokyo box to reveal a left glove immediately tells you the New York box holds the right glove. There is no spooky physics required because the gloves' identities were decided the moment they were packed. If Einstein's glove analogy accurately described reality, then entanglement was a mundane parlor trick of hidden information. But if the quantum mechanics equations were right, the universe allows for invisible, instantaneous connections across space and time. This debate remained entirely theoretical for decades, until 1964, when an Irish physicist named John Bell realized there was a way to actually settle the argument. This chart visualizes what Bell discovered. He calculated a strict mathematical limit, now known as Bell's inequality, that dictates exactly how strongly the measurements of two particles can be correlated if they only rely on classical, predetermined hidden variables. By establishing this hard limit, Bell set a brilliant mathematical trap. If an experiment could somehow produce correlations that exceeded this classical boundary, then Einstein's hidden variables had to be false, and quantum mechanics was the only viable explanation. Bell pulled the discussion out of the realm of philosophical thought experiments and handed it over to experimental physicists. He gave them a concrete way to test whether spooky action was actually real. In 1982, French physicist Alain Aspect built an experiment to put Bell's theorem to the physical test. Aspect's setup fired a high-energy laser into a specialized crystal. A single photon splits into two entangled, lower-energy photons heading in opposite directions. To prevent communication, Aspect rapidly changed the measuring device's angles, the polarizers, while the photons were in flight, closing the locality loophole. Later, physicist Anton Zeilinger expanded on this foundation, running experiments that transmitted entangled photons over hundreds of kilometers using fiber optics, proving that this connection survives outside the tightly controlled environment of a laboratory. Through thousands of iterations, these experiments consistently violated Bell's inequality. They proved that particles do not carry hidden instructions. Instead, they truly exist in an undefined state of superposition, holding multiple possibilities at once, until the exact moment they are measured. In 2022, Alain Aspect, Anton Zeilinger, and John Clauser were jointly awarded the Nobel Prize in Physics, marking the point where quantum entanglement completed its journey from a controversial hypothesis to a proven scientific fact. Validating entanglement revealed that this quantum link is a physical resource that we can harness and control. Financial and military networks are exploring quantum key distribution. It uses entangled photons to generate cryptographic keys, securing communication lines. Because measurement defines an entangled state, an eavesdropper observing the stream alters their condition. The entanglement breaks, instantly triggering a security alert. We are also applying this resource to computing. By entangling multiple quantum bits, or qubits, inside a quantum processor, these machines can perform massive parallel calculations, offering exponential leaps in processing power over classical computers. Looking further ahead, researchers are developing quantum teleportation protocols. Instead of physically moving matter, this process uses entanglement to transfer the exact quantum state of a particle from one location to another, laying the groundwork for a future global quantum internet. It is important to note that this doesn't violate relativity. According to the no communication theorem, because the results of quantum measurements are inherently random, we cannot use entanglement to transmit actual, classical information faster than the speed of light. By confronting the very phenomenon that Einstein found so deeply unsettling, humanity has isolated the mechanics of the quantum realm and begun drafting the architectural blueprint for an unhackable, infinitely connected future.